So in this video, we'll be reviewing composite and inverse functions for the IB Math SL course. Some things we need to know about functions includes domain and range. So domain of a function is everything x can be, where the range of a function is everything that y can be on a function. Domain typically is all real numbers. X can usually be anything, but there are a few functions we've studied where the domain is restricted. Rational functions, which is where you have a fraction that has x in the denominator. These are restricted because your denominator cannot equal 0. It can be positive, it can be negative, but it cannot be equal to 0. So for the domain, you would want to set the denominator not equal to 0, and that would, if you solve it, let you know what x is not allowed to equal. And other than those restrictions, it can be all real numbers. Even root functions, this would be where you have a square root, fourth root, sixth root even. This is where the radicand, the thing underneath the radical, cannot be a negative. It can be 0 or anything positive. So for these, you want to set up an inequality for yourself that the radicand is greater than or equal to 0. And when you solve that inequality, then you'll know what x can be, anything greater than or equal to 4 in that case. Logarithmic functions are also restricted because the argument of a log cannot be negative or 0. So in this case, you want to take whatever your argument is from the log, x squared minus 1 here, and say that it has to be greater than 0, not greater than or equal to, and then solve the inequality in order to determine your domain. Quadratic inequalities, since I just wrote one, it's a good time to review it, can be a little tricky to solve because you'll want to solve it as if it were an equation to a point. So here, where you're about to square root both sides, because there's a plus or minus on the square root that you're about to take, you actually have to split this into two solution regions. One of them, when you do the positive root of 1, you do not flip that inequality sign, but when you do the negative square root of 1, you will flip the inequality sign too. It's sort of like when you divide by a negative on both sides of an inequality, you have to flip the sign. Same thing with doing a negative square root. So here you get an interval, x is greater than 1, or x is less than negative 1 as your two solution regions for what x can be in that logarithmic function. So those are the domains that are restricted that we've studied. Otherwise, it's all real numbers. And then the range, we tend to need a graph for that range. There aren't really rules for. It's just what y values, what function outputs appear on that function. So it's nice to have a calculator in order to do range. You can graph the function and see what y values appear on it. Otherwise, you'll have to imagine simply plugging in or substituting in all of your possible domain values in order to determine what your range values are. So some examples for domain, I have now gone through a few of these. You can see I've put an all real numbers example because it's just linear. Any linear, quadratic, polynomial, etc. is going to be all real numbers. In a rational function, remember the denominator cannot equal 0. So you'll then solve that. And other than the one thing it cannot equal, it's all real numbers. In even root functions, the root has to be greater than or equal to 0. Then you'll solve and you'll see what x can be, greater than or equal to 5 there. And again, in logarithmic functions, the argument has to be greater than 0, and I've been through how to solve a quadratic inequality, so I won't do it again, just to reinforce. Here's asking for domain and range. So if we didn't have a calculator, this could be pretty tricky. So let's attempt to do it without the calculator. Here we have two restrictions going on. It's both a fraction and an even root. So we know that the 9 minus x squared that's inside of that radical would have to be 0 or greater because you can't do the square root of a negative. Though you can square root 0, so you might be thinking that you want to do this until you remember that it's also on the denominator of a fraction, and that means that it probably shouldn't come out to 0 either, because if it does, you'll end up with 1 over 0. So then we erase that equal sign, and this is the most restrictive domain that we could come up with for this function. So then we have another quadratic inequality to deal with here. I think it's okay if you'd like to see your x on the left side as long as you invert the sign with it. And then you'll square root both sides, remembering that when you do the positive root, you don't flip the sign. And when you have a negative root, you do flip the sign. And this time, if x is less than 3 and greater than negative 3, it is more sensible to write your domain like this, with x being between two values. And then range, if we don't have a calculator handy, it's helpful to just imagine plugging in values from your domain, see what kind of outputs you get. You'll see that here, the y, or the outputs, will never equal 0. We have no way to get 0. But because x can be anything between -3 and 3, including very small decimals, 1 divided by a very small decimal would actually be a huge number, like infinity. So y here can go very, very high positive. It can also be a very, very low negative, because x could be negative. The only thing it's not going to equal is 0. So here we want to say, for the range, that y is an element of all real numbers, except for that there's no way to get 0 out of that function for y. Composition of functions. This is where you're putting one function into another. We've practiced it many times. This note is actually wrong. It says fg. That would actually be multiplication if you saw it written just like that. So if you see it with an extra set of parentheses here, like that, that means input the g function into the f function. It can also be written as f open circle g of x, or f of g of x, as I've written it there. So for determining the domain, that's the only tricky part about composing functions. Putting one function into the other and simplifying can be a little bit of algebraic work, but not a trick. But finding the domain of your composition is sometimes tricky, because you'll have to consider both the domain of the final result that you're looking at, as well as the domain of the inner function that you put in. So I think we have an example to see that and why that can sometimes be tricky. So here we have a function g of x and a function h of x. The first order, when it says g open circle h like that, it means to put the h function into the g function. So that means I'd be in order to do g of h of x, I'd be starting with the g function, which is x squared minus 4. But in place of the x, I will be putting the h function, which is root x. And when I simplify that, I have square root of x squared, and that would lift off the square root, and I'd be left with x minus 4. And this is the final composition of the two functions, and it's linear. So you might be thinking that the domain would be all real numbers, but we also have to consider the domain of the inner function, which is the one that we put in. And that one is restricted because it was root x to begin with, and that means x can't be negative. It could be 0, could be positive, but it can't be negative. So even for the composition that we've just come up with, we need to consider that restriction, that x is all real numbers such that it's greater than or equal to 0. So it's half the real numbers. And then for the range of that function, we're imagining, since x can only be numbers like 0 and higher, imagine plugging in 0 to this function, and 1 and 2 and 3 and so on. And you'll see that for the range, y is only going to take values that are greater than or equal to -4. This is basically a line that has a starting point and only goes in one direction. And then h of g of x, just to finish the example, would be to put the h function into the g function. So in that case, we'd be starting with the h function, which is root x, but in place of x, we'll be putting the g function. This time there is nothing really to do to simplify it, so I'm just going to box it and then think about the domain. So the domain of the inner function that we put in, x squared minus 4, that's not restricted, it's all real numbers. But we also do have to consider the domain of the final result, which is a square root function. And for square root functions, we know the radicand has to be greater than or equal to 0. Again, we have a quadratic inequality. When we do the positive square root, we do not change the sign. And when we do the negative square root, we will flip the sign. And we see that x can only take values greater than or equal to 2, less than or equal to -2. That would be our domain. If I put a few added details around it. And then for the range, because it's a square root function, the outputs are all going to be 0 or more, right? Because it's, in the end, you'll be square rooting a 0 or a positive number, so the outputs will always be positive. So for the range, we're going to say y can be all real numbers that are greater than or equal to 0. And I tried to do both of those without a calculator, because those actually, they can be done analytically without a calculator. And then inverse functions. This is where you're switching x and y, and then solving for the new y to get the inverse function. Not every function has an inverse, but the ones that we tend to be asked about on exams do. Any tricks to this? We have 2 facts about inverses. The fact that an inverse function is a reflection of the original function over the diagonal axis, or the line y equals x. So if you were to have I did not mean to move that. Just a minute. If you were to have the function, just trying to erase that check, maybe a function appears like this, and you want to imagine what its inverse is going to look like, you could sketch yourself maybe as a dotted line, this diagonal axis, which is the line y equals x. So basically it has the points 1, 1, 2, 2, 3, 3, 4, 4 on it. If you reflect the original function over that line, so it is sort of like a mirror image, except for your mirror is that diagonal axis, it's going to end up looking something like that. That would be what your inverse function would look like. So you'll notice I did plot a point in order to give myself a little guideline. So basically, if this coordinate was maybe 0, 2, then I knew that the coordinate 2, 0 would be on the inverse function, because it's basically just the switching of all x and y pairs in order to create the graph of the inverse. And then the other trick to inverse functions is knowing that the domain of an inverse is the same as the range of the original and vice versa. So if you are asked for domain and range after you've gotten an inverse function, you should consider the domain and range of the original function and then just switch them. That's going to be the easiest way to go about it. So for example, here we have a function f of x, a function g of x. We are asked in part A just to find the inverse of g of x. So this is a function that has an inverse. So we will start by writing the original function in terms of x and y, and then we will switch x and y. I forgot to switch this to y. We will switch x and y, and then we see that we have a new function. This is the inverse. It's just in a strange order. We like to have our functions written with y by itself. So now we're just rearranging this, and that accomplishes performing all of the inverse operations. So where you see divided by 3, you will have to multiply in order to move it to the other side. And that's how division becomes multiplication in the inverse. I see a positive 1, so I'm going to subtract it. And then I have this negative sign that I don't want. So I multiply through the other side, and now I have my inverse function. It undoes all of the operations of the original function. So we want to call it g inverse. That's the negative 1 that is not an exponent. That is the notation that means inverse function, when you see a negative 1 like that inside of function notation. And then in part B, we're asked to state the domain and range, sorry. So for our original function, domain and range, I'm thinking this is linear, and therefore the domain and range are both all real numbers. And that means that my domain and range here, even when I switch places, domain becomes range and vice versa, are still both going to be all real numbers. It makes our lives a little easier. And then part B asks us to do something sort of surprising, just to mix knowledge together. We're asked to find the solution to this equation. F of the inverse of g of x equals 2. So this is just asking us to apply some things we know. The f of the inverse of g of x means to plug our inverse of g function into the f function, which we haven't yet used, but we'll be starting with, I'm just trying to use the right notation here. We'll be starting with the f function, which is 2 times x plus 4. Only in place of x, we'll be putting the inverse of g function, which is the negative 3x plus 1 that I just found in part A. So if I start to clean this up a little bit, I don't really need those parentheses inside. 1 plus 4 is 5. Then distribute the 2. And that is my composition of those two functions. And I'm supposed to be solving it when it equals 2. So I set it equal to 2. Go about solving, subtract 10 from both sides, and 4/3 is x. So just sort of an interesting algebra application to see if you know what all those different symbols mean. And then, of course, they can find ways to mix topics together. I like this one in that it mixes calculus. You're at first thinking this is a calculus question, and then they give you this sneaky piece of information that you have the inverse of f of 7 equals 1 at some point in this question. So it turns out to be a mixture of calculus with algebra. So here we have f of x equals ax cubed plus bx. We know that at the point, so basically a function where 2 of the coefficients are missing. At the point where x equals 0, the gradient of f is 3. Gradient of the curve, when I'm given a function, I'm thinking calculus. I'm thinking first derivative equals whatever that number is. So I have to get the first derivative of f of x. Now that's f prime, not f with a negative 1. And those notations do look sort of similar, which can mess with your brain if you're in the middle of an exam. So this is just power rule. Bring the 3 down. There's an a there, and we don't know, so we'll leave it and then decrease the power by 1. The derivative of bx is just b. So that's the derivative of the function as best I can get it. And then I'm told that at x equals 0, when x is 0, the gradient of the curve is 3. So I'm going to change x to 0 and set the gradient equal to 3. Gradient is the first derivative. So this whole term is 0, and now I know that b is 3. So I'm halfway there. The question asked me to find a and b to begin with. And then it says, given that the inverse of f of 7 equals 1. So that's a whole other piece of information that I can use on my original function. This means 7 plugged into the inverse. And when you plug something in, it's an x value. But if you're plugging in 7 as an x value to the inverse, you can imagine that that's a y value on your original function. So this would mean basically, I know, a better way to say that. When you see information like this, that means there is an input of 7 giving you an output of 1, but on the inverse. There we go. So you have an x and a y, a 7 and a 1 on the inverse. That means there was a 0.17 on the original. This is just one way to go about doing this problem. I think it's a good, if you really understand what inverse functions are, this is the best way to do it. So if you have the 0.71 on the inverse, you have the 0.17 on the original. And I have an original function I can go up to, and I can substitute 17 in as a point, which helps me as long as I know b, which I do, because I just got it. So 7 equals a times 1 cubed plus 3 times 1. I plugged in 3 for b, and 1 for x, and 7 for y. And then I have an equation that I can use to solve for a. All right, and that is all for this video.